Good afternoon, everybody. My name's Jacob. I'm here with Riley and Don, and today we are going to be talking about Gauss's law in relation to electrostatics. First off, we're going to give a bit of a brief history into Gauss's law and some key points for you guys to understand, and then we're going to dive straight in on how the law can be applied to a long, uniform line of charge. Okay, so Gauss's law is one of the biggest breakthroughs in physics and mathematics of all time. It was first formulated in 1835 by Carl Friedrich Gauss. The equation itself relates to the distribution of electric charge and the electric field of the electric charge. The equation has been extended into Maxwell's four equations of electrodynamics and is considered to be one of the biggest contributions to electromagnetism. Now I'm going to pass it on to Riley, who's going to talk about electric flux.
Gauss's law derives an equation to determine the total electric flux at the surface of an enclosed object. Electric flux is the measure of the electric field through a surface. If there's no charge within the enclosed object, there's going to be no electric field through the surface and there's going to be no flux. Total flux is the amount of flux at an infinitely small area on a Gaussian surface, which we'll talk about later, added with every other flux from every other infinitely small area across the surface. This can be done as it assumes that flux at any point will be equal across a Gaussian surface. When there is excess charge within the enclosed object, the amount of electric flux that moves through the surface is going to be proportional to the amount of charge within the object. If there is charge outside the object, the electric field from this charge will not contribute to the flux through the object itself. So as you can see, this is how the equation is written. And we take the cosine of theta because conceptually, if there's any angle between the surface area and the electric field lines, less flux will occur. So to put this more visually, if we hold a hollow bucket underneath a waterfall and you start tilting the bucket, less water is going to go through the bucket. And this is the exact same concept with the electric field lines and a Gaussian surface.
So what is a Gaussian surface? It is a surface that encloses a charge and is used to simplify the calculation of electric flux. To qualify, it must be a closed surface, the electric field line must pass through it, and the electric field strength at any point on the surface must be the same. Electric flux is the sum of the product of electric field strength in an infinitely small area all added together. The angle at which the electric field goes through the face of the surface area is also taken into account, and to get maximum flux, the face of surface area and the electric field line has to be parallel, or the angle has to equal 0. Electric flux represents the number of electric field lines going through an area. For a Gaussian surface area, it is simpler due to electric field staying constant, leaving only the integral calculation of surface area.
Thanks for that, Don. Now I'm going to be talking about our actual problem. In our example, we have a long straight line that is uniformly charged. We then have encapsulated it with a cylinder. This is because the radius has to be the same at all areas. We know that all the electric field lines point directly out parallel to the cylinder face. This is because the charge is uniform, so every side of a single charge, there will be another charge next to it. This means the only possible direction of the electrical field can be perpendicular to the cylinder, which is parallel to the face. Okay, so we know what the area of the cylinder is, but because of the direction of the electric field lines, we know the top and bottom of the cylinder have zero flux, and there's no electric field flowing through it. Therefore, we can just ignore the top and the bottom of the cylinder's area, which is the shaded area in the image you see, and we only need to incorporate the side, which is the curved area, which isn't shaded. This can be derived as area is equal to 2 times pi times radius times length.
So another very important thing to note is that the electric field lines are going to emit at the exact same angle as the Gaussian cylinder's face at any given time. So this therefore means the angle between the Gaussian cylinder's face and the electric field lines is going to be 0 degrees. Now we can see this in our example on the right hand side image where the electrical field lines are going directly out, and we can see that if you looked at that from a side on sort of angle, the far left example is our example. So understanding this, we can know that theta is going to equal 0 degrees, so we can input cosine of 0 into our equation. So now we conceptually understand what is needed. We can apply this all back to Gauss's law to find out the strength of the electric field at any given distance away from a line of charge. So we first sub back what we know into the equation, the basic equation. We know that the area that is required is only 2 pi times the radius times the length, as we're not going to include the end caps. And we know that cosine of theta is going to be cosine of 0, as we previously discussed about the angle between the electric field lines and the surface area. This is simplified to as you can see below.
Linear charge density is simply the representation of the amount of charge over a given length. It can be calculated by having the total charge, Q in this case in unit of Coulomb, divided by the length of the cylinder in meters. So the relationship between linear charge density and electric field strength is a positive one, as in the more electric charge is in a given area, the stronger its electric field is going to be. Because of this relationship, one can be used to find the others. The link with Gauss' law is that linear charge density can be used to find the electric flux, and then the electric field strength at any distance apart from the Gaussian surface.
Thanks, guys. So to put it in perspective, Gauss's law is a fantastic way to see the interaction of the electric field and the electric flux. It can further be used to find the strength of the electric field at a given distance. Now, I'd like to say a few thank yous to Photius and everyone in the class for making it so enjoyable, even though it's over Zoom, and to my work partners Riley and Don for being very inclusive and hardworking team members. So to that, I'm going to finish by telling you something a very wise physics teacher once told me, and that's physics works. Cheers, guys.